All right. So, sorry for that. So I'd like to talk to you a little bit about the unique challenges associated with manufacturing of perovskite tandems specifically, which is what Swift is focused on. And for some context, we're in quite a different place in the development of our company than Oxford PV. We were only founded in 2017 and have had our first R&D lab in place since 2019. So we are fully focused on the perovskite tandem, and as you all know, it's a multi-layer stack with a wide bandgap perovskite in the front and a low bandgap perovskite in the back. And the performance of those tandems is rapidly increasing. And our team at Swift did some of the early work, and now there's some really great work coming out in the academic community as well, with efficiencies of 25.7, which is really exciting to see. And as you all know, the line of sight efficiency, the practically achievable efficiency for these tandems is over 30%, which is what really motivates us to move forward, especially as the dominating system costs these days are not modules themselves, but are almost everything else. And so raising the efficiency is a key way to lower the LCOE. We think that the all-perovskite tandem sits in a really nice place on the efficiency versus module cost plot. So here we've got a couple different technologies. The 3.5s are, of course, of extremely high costs, but high efficiencies. And then you have some of the other thin film technologies in this bottom left corner where costs are a little lower, but efficiencies aren't so good, and silicon. And then finally, we think with the tandem approach, we can push those efficiencies, the module efficiencies, closer to 30% and get into very competitive module costs. And from the modeling that we've done and that others at the National Renewable Energy Lab in the US have done, the all-perovskite tandem has an opportunity to have the lowest all-in module costs, which we think is extremely exciting. So we, on the path to getting there, we think it's important to not kind of jump the gun, if you will. And so we have a multi-step approach where we think that we're going to start entering the market by developing products that are differentiated, doing things that silicon cannot do. So we're looking at high value applications where the most important metric is not the dollars per watt, but instead is maybe weight or flexibility and efficiency. And so you can look at things that fly, things that move around like cars, and then eventually we move to the rooftop market where there's also a premium on efficiency. And so for some context on the company, just in 1.5 years ago in 2019, this is what our office looked like. We had just leased a building, and the entire inside had to be gutted and redone. And so we had a fold-out table, and that was where we worked for a couple months, just right there. Yep, these were our desks. And then in the meantime, while the building was a construction site, we were actually, we built a little temporary lab in the corner of the construction site with a temporary fume hood and some really makeshift tools to get some work done. And now we have a really nice state-of-the-art perovskite R&D line where we can do any kind of tandem. When we are doing any kind of tandem at high efficiency, and it's great to have this in place now and be able to be fully self-sufficient at the R&D scale. So we've moved from the tent to a really nice lab, and we now are actually at 15 full-time employees and 3 part-time. So how do you actually make a good tandem module? So we need scaled up processing for all the layers, of course. We need good packaging. In our case, we're looking at flexible modules. So it's really important that we use materials to encapsulate the perovskite that don't allow in moisture or oxygen, but stay flexible. And that's it's quite easy to do with glass. It's a bit more of a challenge when you're using flexible front and back sheets. And of course, actually doing the interconnects in a stable way is also important. So there's a couple unique challenges to the all perovskite tandems, I think. If you're putting 2 layers on top of each other, I think anybody who's tried to make an all perovskite tandem will tell you that if you're spin coating one perovskite on top of another perovskite, well, that can be a problem. So you have to work to protect the first layer from the second layer. Or you can develop a deposition method where you don't actually cause any problems to the first cell by depositing the second. For example, a vapor deposited material that doesn't harm the first cell. Ideally, it's compatible with complex compositions because we need to make both wider band gaps and lower band gaps than most people make when they're making perovskite solar cells. So which means we need to include other elements like tin and bromine. And ideally, it's conformal on textured surfaces because, as we've heard in many of the talks, that texturing your cell, whether it's a silicon cell or a perovskite cell, either way, there's some serious advantages in terms of light management. And then, of course, the recombination layer is a critical aspect here. It needs to have minimal lateral conductivity, which also has influence on actually the ability to do module interconnects. And it needs to protect the two subcells from each other. So on the deposition front, at Swift, we've chosen to go with a solvent-free approach. So we're doing all our layers in via vapor deposition. There's, of course, many different ways that you can deposit materials via vapor. I won't say exactly which techniques we're using, but we've had some very nice results with this. We're able to make both sort of the normal sort of mid band gap single junction type band gap materials, wider band gap materials, and low band gap materials, all via this technique. So we've had success in incorporating multiple different precursors, and of course all our materials are methylammonium free from stability standpoint. And then on the left is a kind of a fun picture because we're working on plastics on flexible substrates. You can make these very pretty sort of samples. It's just a little demo, and that's actually extremely thin. We're targeting power densities in the thousands of watts per kilogram, which just is impossible with any wafer-based technology. You need a really thin total cell, which is dominated then, of course, by the plastic encapsulant. And where we've started scaling up our deposition approaches. So on the bottom right, you see a picture of our first iteration of our scaled tool, which lets us run in a linear fashion, lets us run our vapor deposition process for several larger units at a time. And it's working extremely well already. And it's been very exciting for us to bring that online. And it's given us the confidence to actually now, we've already made the commitment to build a small pilot line about 100 to 50 to 100 kilowatts by the end of 2021 based on this technology that we've developed. And I'll say that all our perovskite deposition tools are all built in-house and designed in-house. There's a lot of know-how in the company now on doing that. And this pilot line will be capable of doing both single junctions, all perovskite tandems, and perovskite silicon tandems. Our chosen deposition methods and sample handling are compatible with all three of those. Specifically to all perovskite tandems, there's some challenges associated with deviating from the standards of sort of 1.5, 1.6 EV band gap and going to the lower band gaps. Now you have this extra challenge with stability, especially when there's tin in the perovskite. We've previously shown that actually the exact composition is really important in determining the stability of tin-based perovskites. So if you have half of the B site being lead, you actually completely change the oxidation mechanism for the low band gap perovskites. And this was published a few years ago. The mechanism, in one case, for a pure tin perovskite, you form this tin I4, which has a low activation energy for formation and can leave as a gas very easily. If you have the tin lead alloyed material set, then you actually need to break more metal halide bonds and do not form this tin I4, and the activation energy for that reaction is much higher. So you really slow down that oxidation. And when you choose your composition correctly, and this is not a linear effect with tin content, this is an exponential effect. And if you choose your contacts right, you choose your composition right, and your processing right, then these low band gap solar cells can be extremely stable. And so we have this data that was published in Nature Energy a few years ago as well, where you can actually take unencapsulated low band gap solar cells and have them in an oven at 85 degrees for 1,000 hours and not see any significant drop in performance. And you can also do, which also then means that you can do damp heat testing with encapsulated ones and not see any drops in performance. On the other side, we have the wider bandgap perovskite. I think we've heard a lot in this conference about the challenges there. I'll just say that there are ways to make wide bandgap perovskites that are different from just increasing bromine content, because bromine content can cause problems. And so this was also something published a while ago. And you can see that by incorporating a different A-side cation, we actually can tune the bandgap independently of bromine, and that lets us get to a very attractive range of band gaps for the all-perovskite tandem with quite a low bromine percentage. And that results then in a fairly stable device. And this is again, I think 2018 or so that we did this. Finally, the recombination layer is critical in the all-perovskite tandem. It needs to do several things. It needs to protect the two subcells from each other, both during processing, so that one doesn't, well, if you're doing solution coating, doesn't dissolve the first. But also it also has to stop the two subcells from interacting during operation. So as they get hot, we know that the elements in the perovskites can diffuse. And so you can, for example, if you're not careful, you can have bromine from one subcell migrating into the other subcell, and then your band gaps are changing during operation. And so that's extremely important to mitigate. And the recombination layer is a critical piece in that puzzle. And I just have a note here that ALD is commonly used for this, and that's what you see in the literature. And there's often said, people like to criticize ALD for being an extremely slow process, and that can be true, but it can also be quite a fast process. It's a process that's used now in actually just in silicon cell manufacturing lines to passivate the contacts, and it can be done at speeds high enough that capex is negligible. So it's actually not as, and there are new solutions that it can be roll to roll, it could be sheet to sheet. There's a lot of exciting progress in that area, and we've had some good results on that as well. It's also very difficult to grow a good ALD layer on any surface, and so we found it's important to modify, for example, a fullerene surface, because of course, how can you nucleate, how can you grow a polar substance on a completely non-polar hydrophobic material like fullerene? So you can modify that surface to improve the density of your final layer. If you do all those things, you choose the right materials, you choose the right contacts, and you develop a good recombination layer, then you can make a thermally stable tandem that doesn't degrade over, we've actually now done multiple thousands of hours at 85 degrees. But if you choose the wrong recombination layer, then it can be extremely unstable. So there's, as I said, the recombination layer is critical. Then once you have this kind of result, you can start doing damp heat testing. And so we have done damp heat testing now of our tandems, both glass packaging and flexible packaging, which to our knowledge is the first demonstration of flexible perovskites passing these sorts of damp heat tests. And as others have said, it's important to do multiples of these tests, so that's ongoing. And even more important than doing multiples of the tests is also, I think, doing sequential tests. So for example, doing damp heat testing after thermal cycling to see if any of the adhesion points in the module have failed, and now it's susceptible to moisture ingress. So those are also happening at the moment. And then finally, I think these are more general issues. The supply chain for manufacturing is really important. There's probably a lack of quality control at the moment. That's from the supplier side. And so it's actually not trivial to get reliable and reproducible materials over a long time in large quantities. And so it's important to have many suppliers, all of whom do good quality control. And it's of course also important and helpful for the academic community to help us identify what quality control should look like. And then accelerated testing specific to tandems is also important. So I was very happy to see there's lots of outdoor testing happening. I think that's only a great thing. There should always be more. It's interesting to see Antonio Abate has showed an interesting talk 2 days ago, I think, where seeing a difference between stable output and cycling behavior. That's a fascinating thing to study. And then combining stressors. So light only or heat only are quite simple tests, quite easy to do. Combining all these stressors is more challenging. And so these are all important aspects to be studied. I'll also add that for the outdoor testing for tandems, there might be unique behaviors there that wouldn't exist for single junctions. If the two subcells have different ideality factors or have different shunt resistances, you might see real problems. Oh, yeah, and so today, this is our team. So I'd like to thank everybody on the Swift team. We're from 10 different countries, and been working hard and making rapid progress. It's been really fun. And I'd like to thank our advisors. We're lucky to have Atia, former CTO of Mia Soleil, and Chris Norris, former CEO of Alto Devices, and of course Vladimir Bulovich and Mike McGeehee, our previous postdoc and PhD advisors. And we've worked closely with NREL, so I'd like to thank our collaborators there also. Thank you.
Yes, thank you, Thomas, for this impressive talk. And yes, there are a couple of questions, but because of time constraints, again, we cannot answer them all. But maybe one question regarding octahedral tilting. Hopefully you've heard about it. Did you observe something like this in your devices?
Octahedral tilting?
Yes.
Of the lead halide octahedra, I imagine. Yeah, I suppose many perovskite materials, especially if they're in the tetragonal phase, will have octahedral tilt. That, I guess that's kind of in the. It's also an interesting way of tuning the band gap, actually, using octahedral tilting. Oh, I imagine this is referring to maybe the DMA incorporation. Yeah, yes, octahedral tilt is a very important parameter for the band gap, because I think as most of you know, it's not just orbital overlap, not just the frontier energy levels of the metal and halogens that determine the band gap. It's also the orbital overlap. So as your octahedra tilts, your orbitals overlap more or less, and so that affects the band gap. That can lower the valence band in these anti-bonding type structures. So yes, we do see that, and you can exploit that to change the band gap.
You said that you are now concentrating more, let's say, on niche markets, what silicon cannot do. Do you think that even in further future you could go even to utility scale for large systems?
Yeah, absolutely. That's 100% the goal. We think it's very difficult to enter the market on a dollar per watt sort of level, but we think ultimately the all-perovskite tandem has the potential to be both extremely efficient and the lowest cost solution, not just at the module level, but also at the system level. Because if the system is dominated by the installation racking and labor, then you can imagine that a lighter module that can be installed in different ways has some real advantages, both for rooftop and utility scale. So that is definitely our long-term vision.
Okay, thank you very much. And so please answer the questions in the chat, and also please the people who answered, go into the chat also after that, because let's say the speakers will also answer the questions after the session. So because now they also would like to hear maybe the other